Good morning. Sorry I'm not there again today, but hopefully y'all did wonderful on the quiz. So this was the next thing that we were gonna do, symmetry. So take a second and try to answer the first 9 questions, and then we'll come back. So pause the video and try to answer about symmetry. Alrighty, so symmetry you learned about in geometry. So it's how like proportion people are in balance. It's very such as you can see Anne Hathaway over there. Her face is very symmetrical. There's even research that says that we rate symmetric faces as being more attractive. Today, we will investigate further what it means for functions to be symmetric. So, the graph of x squared minus 2 is below. What do you notice about the symmetry of f of x? So, it has y-axis symmetry. So, it looks the same on the left as the right. So it has, so what this means is that f of x is an even function. So when we're even, we have y-axis symmetry. So filling in table number 2 tells us that as well. So for the function at -4, when I plug in -4 inside this function, I get a 14. When I plug in a -2, I get, what, a 2. When I plug in a 0, I get a -2. When I plug in a 2, I get positive 2. And when I plug in a 4, I get a 14. So what do you notice about the ordered pairs here? So this ordered pair right here, so -4, comma 14 looks very similar to when I plug in a positive 4, right? It's symmetric there. Also with a -2, same thing is happening, right? I've got a positive 2. Oops. And when I plug in a positive 2, I get a 2. So what do you notice about that? So the outputs are the same. So when I'm putting in the opposite x values, they give the same y value. So that is another definition of being an even function. So when I plug in a negative version of my x value, it's going to give me the same thing as if I put in the positive version. All right, so given an equation of a function, how could you check if the function has y-axis symmetry without looking at a graph? So just like I said, so plugging in the opposite. So plugging in the opposite x values. Alrighty. So number 5 here. So number 5, what do you notice about this one? So the graph is x cubed minus 4x is below. So what do you notice about this graph? So it doesn't have y-axis symmetry, so I can't draw a line. But I want you to take your piece of paper and I want you to rotate your piece of paper 180 degrees. So I want you to rotate it 180 degrees. Does it look the same? So if you rotate your piece of paper, does the graph look identical? Okay, it does. So if you rotate 180 degrees, the graph would be the same. This is called origin symmetry. So g of x here is an odd function. This is called origin symmetry. Alright, so when you plug in a -4, you get a -48. When you plug in a -1, you got a 3. Plug in a 0, you get a 0. When you plug in a 1, you get a -3. And when you plug in a 4, you get a 48. So what are you noticing here? So what are my patterns that we notice here? So -4 and 4 give opposites. So opposites produce opposites. So 4 and -4 give opposites. Alright, so given an equation of a function, how could you check if the function is symmetric across the origin without looking at the graph? So we could plug in opposite x values. So when you plug in opposite, and see if you get, when you plug in the opposite x values, see if you get opposite y values. So this means that this one is a little different. So when I plug in opposites, I'm actually going to get an opposite of what if I plug in a positive answer. So if it's an odd function, you're not going to get the same value, but you'll get the opposite. So looking at Anne Hathaway's face, looking at that photo, what type of symmetry does Anne Hathaway have? So what do you think? What do you think? Her eyes kind of start, so don't you think she's pretty symmetric? So she's very symmetric. Alrighty. So let's talk about even and odd functions. So a function is even if it has y-axis symmetry. So an example of that is my parabola. That means that if I drew a line on the y-axis, the left side would look identical to the right side. And these values are the same. So the points here are the same if I'm plugging in a negative and a positive. So remember, if you plug in a positive value, you're going to get the same thing as if you plug in a negative. All right, a function is odd if it has origin symmetry. So that means rotate 180 degrees. And it looks the same. So an example of that is our cubic function. So I have a positive. If I plug in a positive x, I get this y. If I plug in a negative x, I'm going to get the opposite of that value. So if you're plugging in a negative, you're going to get a negative output. Okay. All right, so to prove symmetry algebraically, plug in, so you'll plug in negative x into the function and simplify. And then you'll just compare the two functions that you get. You'll compare it to the original. If it's got the same operations, so if it's got the same operations, then it would be even. If it's all negatives, then it would be odd. All right. So take a second and see about if you can do these check your understanding problems. So pause the video and come back. All right. So I try my best to half of number one. So number one is an odd function. So sketch what it would look like. So odd would be rotational, right? So at this point 0, so at the point 0, 3, we would actually be at 0, negative 3. And instead of being at 3, 0, we're going to be over here at negative 3, 0. Instead of being at 5, negative 1, we're going to be at negative 5, negative 1. Instead of being down here at 7, negative 2, we're going to be at a negative 7, but I'm going to plug in a negative 2. All right. If 3, negative 18 is on the graph of an even function, what other point is guaranteed to be on the graph? So if it's on an even function, that means if I plug in a negative 3, I would get a negative 18. Okay. All right, so for number 3, I kind of wanted to go through this one together. So number 3, I've got this crazy function. Is it an even, an odd, or neither? Prove your answer algebraically. So if I plug in a negative x right there for my x, I'm actually going to raise that negative x to the 5th power. So when I do that, that becomes a negative x to the 5th. So a negative times a negative times a negative times a negative times a negative. So that's still going to make it a negative on the outside. A negative x to the 3rd. That's 3 negatives. So that means it's going to be a negative. It's going to be the same thing as a negative x to the 3rd. And then nothing's going to happen to my positive 3. So to be an even function, that means it's got to be identical to the original function. But all my signs, these two signs are opposites. To be an odd function, all of my signs would need to be an opposite, so they would all need to be negative, right? So this one's going to be neither because I have this this positive right here. So I have this one positive back here. So this one's going to be neither. All right, true or false? If the statement is true, explain why. So all even functions go through the origin. So that's false. So think about a translation, a shift of the graph, the parabola up or down on the x-axis. It's still going to be an even function, but it's not going to go through the origin. If each term in a polynomial function has an even exponent, the function is even. So let's think about what we did in number 3. So that's got to be true, because anytime that you raise a negative x to a positive or to an even exponent, it's going to make it positive. So it would be equivalent. So this is meaning like if everything in the polynomial is even, so you don't have a constant term. So if you have something that looks like this with no constant term. Okay. All right, so that's even and odd functions. So we've kind of really talked about this prior to, like we talked about the axis of symmetry with our parabolas, but now we're actually given it a formal definition. So on Monday, we'll do parent functions. So we'll do parent functions where we're going to put all of this together. So if you will, just do your book problems for this. That would be awesome. And I'm hoping that I will see all of y'all Monday morning, bright and early. All right, y'all have a fabulous weekend.